Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 14, 2025, just 2 days ago. The striking result is a search-driven simulation that automatically uncovers long-tail, multi-turn privacy attacks and then co-evolves stronger defenses, revealing tactics like impersonation and consent forgery, and countermeasures like identity verification state machines. The paper is titled, Searching for Privacy Risks in LLM Agents via Simulation. And as we will see later, the implications for deployed agent ecosystems are significant. Beyond discovery, the work shows transfer of attacks across models, benefits from parallel search, and a practical path to proactive mitigation. Building on that, tweets highlight evolving attacker and defender strategies in simulated agent interactions, stressing privacy risks and state machine defenses. Engagement looks moderate, with dozens of likes and a few replies. Alright, this figure walks through the pipeline end to end. At the top, configuration turns a written privacy norm into agent instructions and app environments. In the middle, simulation shows the attacker and defender exchanging messages, with leaks only counted when a tool action transmits sensitive information. Moving down, the search loop feeds simulations into an optimizer that proposes new prompts. Finally, the timeline illustrates co-evolution. Attacks escalate from fake urgency to impersonation, while defenses progress from simple rules to identity-checked state machines, driving leakage down. Next, the diagram contrasts attack search on the left with defense search on the right. Focus on the whole graphic first. Parallel threads N each test M simulations per attacker instruction, then the best candidate gets P extra runs for a reliable score, before optimization proposes the next instruction. Building on that, dashed cross arrows indicate cross-thread propagation, where the top-performing trajectories are shared so every thread can refine the strongest idea. Meanwhile, the defense side runs a single sequential loop across scenarios for comprehensive coverage. Moving to the results, this chart and table together narrate the co-evolution. The red line traces average leak scores across phases, climbing from direct requests to impersonation, then dropping once identity checks arrive. Below, the left column names the strategies, and the right column shows concise instruction snippets, with red highlights marking the new attacker tricks, and green highlights marking stricter defender rules. Taken together, the trajectory shows A0 to D2, with impersonation as the turning point, and the state machine closing the gap. Okay. This table benchmarks basic instructions across attack and defense backbones on the testing 100 set. Focus first on the overall grid, which reports average leak score and leak rate. The standout pattern is asymmetric gains. Swapping in a stronger defense backbone drops leak score sharply. For example, 4.1 mini to 4.1 defense goes from 31.2% to 16.5%, while stronger attack backbones barely help. Building on that, leak rate is typically 5 to 10% higher than leak score, reflecting faster disclosures. Now, this ablation figure compares 4 knobs of the search process, each plotting leak score over search steps. First, look across the full panel to see consistent rises as the search uncovers stronger attacks. In the left plot, more parallel threads speed early gains, but benefits taper without information sharing. Moving right, adding cross-thread propagation sustains progress, while oversharing every step hurts diversity. Next, a stronger optimizer with deliberate reasoning drives the largest jumps. Finally, different defender backbones change difficulty, with mini and nano leaking faster. Alright, this table reports cross-model transfer of discovered attacks and defenses, with cells showing average leak score and percent. Focus on the full grid first. Rows vary the attacker backbone, columns list defense backbones, and the co-evolve stages A0D0 through A2D2. Building on that, the gray first row is the original configuration, while the other rows show transfers. The key pattern is asymmetric transferability, where swapping defense models changes outcomes more than changing attacker models. Next, this heat map summarizes how each attack level interacts with each defense, reporting average leak scores as percentages. Focus on the full grid first. Green cells mean low leakage, while red cells indicate high risk. Notice the standout red block at A1 versus D0, showing 76% leakage, and the milder 7.1% at A2 versus D2 after state machine checks. Building on that, the rows and columns also list marginal averages, highlighting A2 as the strongest attacker and D2 as the most resilient defender. Building on that, 2 takeaways stand out. Adversarial co-evolution in simulation surfaces long tail, multi-turn privacy attacks, and identity-verified state machines sharply cut leaks without killing usefulness. A state machine here means a step-by-step protocol that only proceeds after strict checks. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.